Since inspection of welds using ultrasound is a leading-edge technique for finding in-weld flaws, it is important that those involved with welded fabrication have some knowledge of the method and its application. The basic ultrasonic equipment consists of a power source with CRT screen, probes and calibration blocks. Ultrasonic waves are generated by applying electric current from the power source to a probe. The probe contains a piezoelectric crystal such as quartz. The piezoelectric effect allows conversion of electrical energy to mechanical energy. The mechanical energy is then transmitted through the material under test, and any energy that is reflected is returned to the probe, converts back to electrical energy, and is then transmitted to the ultrasonic equipment. To transmit the sound energy into the material, the air gap between probe and metal must be eliminated. This task is performed by using a couplant, usually oil, grease or water. The calibrated CRT screen displays the history of the transmitted ultrasonic waves. Principally, these are the distance the sound travels or time base, shown on the horizontal axis, and the amplitude of any reflector, given on the vertical axis. Prior to testing a weld or other component such as a casting, the equipment must be calibrated on a block which is of the same material and contains known dimensions and hole sizes. Here, the technician is calibrating the horizontal sweep on the CRT time base as a multiple of 25 mm, the thickness of the block. There are two types of ultrasonic beam modes usually employed in the testing of welds. These are longitudinal or normal waves and shear or angle waves. The direction of a longitudinal wave is normal to the surface being inspected, and that of a shear wave at an angle. When a change occurs in a material, such as a void caused by a flaw, an acoustic mishmash occurs, and some of the sound energy is reflected back to the ultrasonic probe, converted into an electrical signal, and this is then electronically displayed on the CRT screen. It is usual to investigate a weld using a shear wave probe, as the angle allows the operator to stand off to the side of the weld, avoids the weld build-up, and allows the operator to select a probe angle that will strike the fusion line of the weld preparation at approximately 90 degrees. The fusion line being a likely location for in-weld flaws, such as lack of fusion or trapped inclusions. By reference to the calibration carried out on the test block, the position, length and depth of the flaw in a weld can be analysed from the data given on the CRT screen. Accurate sizing and positioning of flaws is one of the great advantages of non-destructive testing when using ultrasound. This helps with decisions on how to facilitate a weld repair, and also defect sizing plays a critical role in the analysis of structures using fitness for purpose techniques.